In this lesson you will learn about inverse functions. To illustrate an inverse function, I'm going to start with the equation f of x equals 2 to the x. And I'm going to make a table of x values and substitute them into the function to find their corresponding y values. And the values that I'm going to pick are -2, -1, 0, 1, and 2. And when I take each of these values and substitute them in for x, 2 to the -2 is 1 over 2 squared, which is 1/4. 2 to the -1 is 1 over 2 to the first, which is 1/2. 2 to the 0 is equal to 1. 2 to the first is 2. And 2 squared is 4. So the 5 points on f of x equals 2 to the x are -2, 1/4, -1, 1/2, 0, 1, 1, 2, and 2, 4. So if I take these 5 points and identify them on f of x equals 2 to the x, I have -2, 1/4, -1, 1/2, 0, 1, 1, 2, and 2, 4. Connecting these points forms this curve. So some properties about this curve is that the domain is all real numbers. I could have chosen any values for x. The range, since this graph sits entirely above the x-axis, the range has to be positive, and it's all values that are greater than 0. Another property of this graph is that we have a y-intercept, and the y-intercept is 0, 1, and this also has a horizontal asymptote, and the horizontal asymptote is the equation y equals 0, just the x-axis. Now what I'm going to do is I'm going to take these points and flip them around so that I have 1/4 -2, 1/2 -1, 1, 0, 2, 1, and 4, 2. And now I'm going to plot them on this curve, and when I do, I see that they form this curve. And if you connect the points, you'll get the graph of the function log x with a base of 2. So some properties about this graph is that the domain are x's that are greater than 0, since the graph sits entirely to the right of the y-axis, but the range are all real numbers because it uses values above and below the x-axis. This graph has an x-intercept of 1, 0, and it has a vertical asymptote of x equals 0, just the y-axis. So notice how in 2 to the x and log of x base 2, everything is interchanged. For 2 to the x, the domain is all real numbers, but in log of x, the range is all real numbers. In 2 to the x, the range is greater than 0, but in log x, the domain is greater than 0. The intercept is switched, and the asymptotes are switched as well. When you have this property of functions, the functions are said to be inverses of each other. And the symbol for inverse is f to the -1 of x, and this is read f inverse of x. Another property that inverse functions have is that they are symmetrical around the line y equals x. So think of this line y equals x as a mirror, and each curve is reflected over it to get the inverse function. To find the equation of the inverse function, if we go back to f of x equals 2 to the x, I will write this as y equals 2 to the x, and to find the equation of the inverse, I switch x and y, the same way I switch their points. And after switching x and y, I next want to solve for y. So to solve for y, since I have a base of 2, I take the log with a base of 2 on both sides of the equation so that it cancels on the right side of the equation, and I'm left with log base 2 of x equals y, and then we substitute the symbol for the inverse function in, which is f inverse of x equals log base 2 of x. So first let's look at some definitions, and the first one is the vertical line test. The vertical line test is used to determine if the graph is a function. And if I draw a vertical line through any point on this graph, the vertical line will never touch the graph more than once. So therefore, this is a function. The same with this next graph. Any vertical line that's drawn through this curve will never touch more than once. So it's also a function. The horizontal line test is used to determine if a function is one-to-one. So it must be a function first. And this first graph, if I draw a vertical line, it fails the vertical line test. So if it's not a function, then it can't be one-to-one. Whereas the second graph passes both the vertical and the horizontal line test. So it is a function and it is one-to-one. So if we look at one-to-one functions, a one-to-one function is a graph that passes both the vertical and horizontal line tests. So if a function is one-to-one, then we know that the graph has an inverse. So in this first graph, we can see that it passes both the horizontal and vertical line tests. Same with the second graph. And the third graph, even though it has asymptotes, it still passes the vertical and horizontal line tests, so it's also one-to-one. The next definition is monotonic. And a monotonic function is one that is always increasing or always decreasing. So looking at the graph above, this graph here is always increasing, except at this point here where it has a horizontal tangent. As long as your graph does not have a combination of increasing and decreasing, it's okay to have a horizontal tangent, but it must either always be increasing or always decreasing at every other point. This graph is monotonic. The second function is also always increasing, at a much slower rate, but it is still increasing. And this third graph, even though it is not continuous and we have two separate branches, each branch of the function is decreasing. So since both branches are in the same direction, it's always decreasing and it's monotonic. So to look at a graph, it's very simple to determine whether or not it's monotonic. On this first graph, this parabola, we see that it's decreasing on the left side of the y-axis, but increasing on the right side of the y-axis. So therefore, it is not monotonic. But to show this algebraically, since increasing and decreasing have to do with the first derivative, I'm going to take this function's equation, f of x equals x squared minus 2, and I'm going to find f prime of x. And since I get the derivative to be 2x, if I found f prime of negative 1 and f prime of 1, negative 1 would give me negative 2, and positive 1 would give me positive 2. So a negative derivative means that it's decreasing, and a positive derivative means that it's increasing. So if you had to show this algebraically, you would want to show that depending on the value of x would change the direction of the curve. Whereas in the second graph, we can look at this and see that it is always increasing. So when we find the first derivative, that should confirm the graph. And we get 3x squared. So x squared, whether we substitute a negative value in for x, or a positive value in for x, or a fraction or a decimal, it will always give us a positive answer. So our first derivative is always positive, our graph is always increasing, so therefore it's monotonic. And the last thing that we'll look at before we start the examples are how to determine or how to verify that functions are inverses. And we will use this definition, f of g of x, test to see that it's equal to g of f of x, and they both have to equal x. So I'm going to start with f of g of x. So I take my function f, which is x cubed, and I take g and I substitute it in for x. So I take the cube root of x and I cube it. And the cube and cube root cancel each other, so I'm just left with x. The second part of the definition that I have to show is that g of f of x is also equal to x. So I take my function g, which is the cube root of x, and now I take f and substitute it in for x in g. So when I substitute x cubed under the cube root, the cube and cube root cancel each other, and again I'm left with x. So this is how you verify that two functions are inverses of each other. For questions 1 through 7, we're asked to determine if the function has an inverse. And we're going to do this in two ways. We're going to do this graphically and algebraically. So the first thing I want to do is look at my original function, f of x equals negative 3x plus 1, and state the domain. The domain of this function is all real numbers. We just have the equation of a line. And if we look at the graph, we see that the graph is always decreasing. So we know that the answer will be yes, that it has an inverse because it's monotonic, but to show it algebraically, we take the first derivative. And the first derivative is equal to negative 3. So if it's equal to negative 3, then it is always decreasing, and therefore monotonic. And if it's monotonic, it has an inverse. For number 2, f of x equals x plus 1 over x minus 1. In this example, the domain x cannot equal 1. If x is 1, your fraction will be undefined. So if we look at our graph, we see that each branch is decreasing, and we can also see that it passes both the horizontal and vertical line tests. That's another way we could check this graphically. So we know again that the answer will be yes. But to show this algebraically, I want to find the first derivative, and this derivative involves the quotient rule. Starting with the derivative of the numerator is just 1, times it by x minus 1, and then minus the derivative of the denominator times the numerator over the denominator squared. And simplifying, we have x minus 1 minus x minus 1 over x minus 1 squared. The x's cancel, and f prime of x is equal to negative 2 over x minus 1 squared. So the numerator of the first derivative is negative, and the denominator will always be positive because it's being squared. So therefore, a negative first derivative is always decreasing, and therefore it's monotonic and has an inverse. For number 3, f of x equals the square root of 2 minus x. So if we take 2 minus x, 2 minus x must be greater than or equal to 0 so that the radicand is not negative. If I add x to both sides, I have x is greater, or 2 is greater than or equal to x, so our domain is that x must be less than or equal to 2. So looking at the function, we can see by the graph that it is always decreasing, and so we know by graphically that this will have an inverse. To show this algebraically, we will take the first derivative, and I will rewrite f of x as 2 minus x to the 1/2, so that f prime of x is 1/2 times 2 minus x to the negative 1/2, and then the chain rule times negative 1, so that the first derivative simplifies to negative 1 over 2 times the square root of 2 minus x. So the numerator of the derivative is always negative, and the denominator will always be positive because of the domain. So a negative numerator and a positive denominator will give us a negative value, and a negative first derivative is always decreasing. Always decreasing means that it is monotonic and therefore has an inverse. For number 4, we have f of x equals 2x squared minus 3. Now this domain is all real numbers. You always want to look for the domain because sometimes you're given a function and it may tell you to only use x's that are greater than or equal to 0. If that were the case, we would just be focusing on the right side of the parabola. But on this one, we just have the full equation 2x squared minus 3. And looking at the graph, we see that the left side of the y-axis is decreasing and the right side is increasing. So algebraically, it should confirm that this graph is not monotonic. We could also tell by the horizontal line test that it fails. So if we find f prime of x is equal to 4x, and if I take f prime of negative 3, you can pick any numbers you'd like, and then f prime of 3, the derivative will give me a different sign, and since the signs are different, this tells me that it's decreasing, this tells me that it's increasing, therefore it's not monotonic. And if it's not monotonic, it does not have an inverse. For number 5, f of x equals the natural log of x. The domain of the natural logarithmic function are x's greater than 0. So looking at my curve, this curve is always increasing, and so algebraically we should be able to confirm that by taking the first derivative, and when I find f prime of x, the derivative of the natural logarithmic function is just 1 over x. Now normally a derivative of 1 over x, substituting in a negative value for x, would give you a negative first derivative, and a positive value for x would give you a positive first derivative. But our domain are x's that are greater than 0, so for that reason we can only substitute in positive values, and this graph is always increasing. And if it's always increasing, it's monotonic, and it has an inverse. So always be aware of the domain. If the problem gives you the domain, you can only check those values in the first derivative. Otherwise, you have to find it yourself. For number 6, we have a polynomial function, and the domains of polynomials are all real numbers. So looking at the graph, I see that it's increasing on this side, decreasing here, and increasing here. So we know that when we check this algebraically, this will not be monotonic, and therefore it will not have an inverse. So let's start by finding f prime of x, and for f prime of x, we get 3x squared minus 1. And if I pick a value for x, let's take f prime of 0, and another value of x, we'll pick f prime of 2. And these two values I chose because by looking at my graph, I see that when I substitute in 0, I see that that portion of the graph is decreasing, but when I substitute in 2, it's positive, so it's increasing. So therefore, it is not monotonic and does not have an inverse. And for number 7, we have f of x equals tangent of x. So when we find the domain for the tangent of x, we know that tangent of x has asymptotes at pi over 2, 3 pi over 2, 5 pi over 2, basically at all values where cosine is 0. And notice how all of the numerators are odd numbers, 1, 3, 5, and the next one would be 7 pi over 2. So to express an odd number, we can write either 2n minus 1 or 2n plus 1 times pi over 2. So this expresses our asymptotes as an expression. So we would say that the domain x cannot equal 2n minus 1 times pi over 2. So looking at this function, it does fail the horizontal line test, but each part of the function is always increasing. So let's see what happens when we solve this algebraically. So f prime of x is the derivative of tangent x, which is secant squared. And since we're squaring a function, anytime you square a derivative, it's always positive. But we're looking at the graph and we see that it fails the horizontal line test. So here's what we'll say for this one. We will say that this function is always increasing and is monotonic, therefore has an inverse, in an interval 2n minus 1 times pi over 2 to 2n plus 1 times pi over 2. So if you pick a value for n, say 1, you have 1 times 2 minus 1 is pi over 2, and then use that same value in for 2n plus 1, and you get 3 pi over 2. So therefore, you would be looking at just one branch of the curve. So it only has an inverse when you're looking at one part of the tangent curve. So now, for numbers 8 through 12, we will actually find the inverse. So number 8 is the same equation as number 1, where we knew that it had an inverse. Now we're just going to find the equation. So I start by writing this as y equals negative 3x plus 1, and I interchange x and y so that I have negative 3y plus 1, and I solve for y. So I subtract 1 from both sides. X minus 1 equals negative 3y, and when I divide everything by negative 3, I'm now going to write the y on the left side. I have y equals negative x plus 1 over 3. I just move the negative up, and I just put the inverse symbol in, f inverse of x equals, and you can leave it as negative x plus 1 over 3, and you can also write this as negative 1/3 x plus 1/3. So this is the equation of the inverse. For number 9, we have y equals 3x plus 1 over 2x minus 1. So I start by writing this as y equals, and then I interchange x and y, and then I cross multiply, I distribute the x, okay, so now that we have all of our parentheses and fractions removed, our goal is to solve for y. So what I'm going to do is I'm going to get all of the y terms on one side and everything else on the other. So I'm going to bring this term over here and this negative x over here, so that my new equation is 2xy minus 3y equals 1 plus x. And by doing this, I can't combine these two terms, but what I can do is factor out a y so that I have 2x minus 3. And you can also write x plus 1. X plus 1 or 1 plus x are the same. And as a final step, I divide both sides by 2x minus 3 so that I get x plus 1 over 2x minus 3. And if I put my inverse symbol back in, f inverse is equal to x plus 1 over 2x minus 3. Before I go on to number 10, I would just like to show you something different that could happen with this problem. When we're at the step 2xy minus x equals 3y plus 1, what I could have also done is, instead of bringing the 3y to the left and the negative x to the right, I could have brought the 2xy to the left, or to the right, and the 1 to the left. If I had done that, I would have negative x minus 1 equals 3y minus 2xy. I still can't combine my y's, but I can factor the y out, and I have 3 minus 2x. And when I divide both sides by 3 minus 2x, I have y equals negative x minus 1 over 3 minus 2x. And when I put my inverse symbol in, I have an equation that's different than the one I wrote in red. So if you did it this way, it's not incorrect. It's just that you reverse the direction that you move the terms after you cross multiplied. The only difference between the answer in red and the answer in blue is that all of the signs are switched. The signs in the numerator are negative, and the negative and positive were reversed in the denominator. So both of these answers are correct. It just depends which direction you move your terms. For number 10, we have y equals the square root of 2 minus x. And I start by interchanging x and y so that I have x equals the square root of 2 minus y. And then I will square both sides so that I can solve for y, so that I get x squared equals 2 minus y. And if I add y to both sides, I get y plus x squared equals 2. And then subtract x squared gives me negative x squared plus 2, or 2 minus x squared. So the equation of my inverse is negative x squared plus 2. So we know from some of the graphs that we saw earlier that parabolas do not pass the horizontal line test. So if I go back to the beginning of this problem, the square root of 2 minus x, and find the domain, 2 minus x has to be greater than or equal to 0. And if I solve for x, I get 2 is greater than or equal to x, which gives me a domain of x is less than or equal to 2. So if x is less than or equal to 2 in the domain, our range are y's that are greater than or equal to 0. So since these are inverses, the domain of the inverse is the range of the function. So my x has to be greater than or equal to 0. I must include that in the equation of the inverse to show that we are not using the entire parabola, just the right side. So for number 11, we have y equals 2x squared minus 3, and we start by interchanging x and y, and I solve for y. I'm just going to move the 2y squared onto the left side of the equation, and I have 2y squared is x plus 3, and we get y squared is x plus 3 over 2. So to solve for y, I take the square root of both sides, and this gives me y equals plus or minus the square root of x plus 3 over 2. Since our domain in the original problem was x is greater than 0, or x is greater than or equal to 0, then we only want the positive square root, so it's the positive square root of x plus 3 over 2, and then we just put the symbol back in for the inverse function. So f inverse is equal to the positive square root of x plus 3 over 2. And for number 12, we have y equals the natural log of x. So if I interchange x and y, I have x equals the natural log of y. So we have to solve for y still. And to solve for y, you want to remember that the base of a natural log is equal to e. So we have to get this out of logarithmic form and put this in exponential form. So I take my base and raise it to my answer, and I get e to the x. It is equal to the argument, which is y. So my equation is y equals e to the x. And then all I have to do at the end is put my symbol for the inverse back in. So f inverse is equal to e to the x. For question 13, we want to show that the functions are inverses of each other. So to show that functions are inverses, we're going to start by finding f of g of x. And we want to make sure that f of g of x is equal to x. So I'm going to take my function g and substitute the entire function into x. So I have 1 over, instead of having x minus 2, I have 2x minus 1 over x minus 1 minus 2, and then I have a plus 1 on the outside. So I'm going to put this over 1 and multiply by the common denominator of x minus 1 and I have 1 over 2x minus 1 minus 2 times x minus 1 over x minus 1, and then I have this plus 1 on the side, which is 1 over 2x minus 1 minus 2x plus 2 over x minus 1 plus 1. And continuing algebraically, my 2x's cancel, 2x minus 2x, and then negative 1 plus 2 is just 1 over x minus 1. And then I have this plus 1 still. Multiply by the reciprocal of that complex fraction, and I have x minus 1 over 1 plus 1 is x minus 1 plus 1, which simplifies to x. So far, the first part of the definition is working. We have f of g of x is equal to x. Now we have to show that g of f of x is equal to x. So for g of f of x, I'm going to take the function f, and it's going to get substituted in for this x here and this x here. So instead of 2x minus 1, I have 2 times 1 over x minus 2 plus 1 minus 1. And instead of just x minus 1, I have 1 over x minus 2 plus 1 minus 1. So if I distribute the 2, I have 2 over x minus 2 plus 2 minus 1, and then over, at least these 1's cancel, and I just have 1 over x minus 2. I can combine the 2 and the 1 to 2 over x minus 2 plus 1 over 1 over x minus 2. If I place this over 1 and get a common denominator of x minus 2, I have g of f of x is equal to 2 plus x minus 2 over x minus 2 over 1 over x minus 2. Whenever the denominators are the same in a complex fraction, you can cancel them. So I just have 2 plus x minus 2 over 1. The 2's cancel, and I'm left with x over 1, which is just x. So since both f of g of x and g of f of x both equal x, that's how we verify that two functions are inverses. So the last thing that we will do in this lesson is look at how to find the derivative of the inverse function at a particular point. So this is the formula of how to find the derivative of the inverse, and these are the steps. So we're going to follow these 3 steps. So for 14 and 15, we're asked to find the derivative of the inverse function at the certain value of a. So for number 14, we're given f of x equals the natural log of e to the 3x over x minus 1. And this function may look complicated with the natural log of e, but using properties of logs, we can bring that 3x in front, then the ln of e cancels, so we actually just have f of x equals 3x over x minus 1. So scrolling down, I'm going to start with step 1, and step 1 is to set f of x equal to a and solve for x. So that means take 3x over x minus 1 and set it equal to a, which in this example is 2, and solve for x. So to solve for x, I will cross multiply, and I get 3x equals 2 times x minus 1, and I get 3x equals 2x minus 2. And when I solve for x, I get x equals negative 2. So that's step 1. Now for step 2, I'm going to scroll back up. We want to find f prime of x at the value of x found in step 1. So that means we'll be finding f prime of negative 2. So to find f prime of x, I have to use the quotient rule. And f prime of x would be equal to 3 times x minus 1 minus 1 times 3x over the denominator squared, x minus 1 squared, and simplifying this, I have f prime of x equals 3x minus 3 minus 3x over x minus 1 squared, and this simplifies to f prime of x as negative 3 over x minus 1 squared. So to finish step 2, I have to find f prime of negative 2, and negative 2 was the answer from step 1. So we have negative 3 over negative 2 minus 1 squared, which is negative 3 over negative 2 minus 1 is negative 3, and then squared is 9, which simplifies to negative 1/3. So for step 3, our final step, I won't scroll up for this one. It just says to take the reciprocal of step 2, which is negative 3. So the derivative of the inverse at a equals 2 is equal to the reciprocal of step 2, which is negative 3. And our last example, we want to find the derivative of the inverse at a equals 4, and starting with step 1, I take x cubed minus x squared plus 2x plus 2 and set it equal to 4. So when I bring over the 4, I get minus 2 equals 0. And now with this equation, I will use factor by grouping because I have 4 terms. And when I take out an x squared of the first 2 terms, I have x minus 1. And of the last 2 terms, I take out a positive 2. So that the common factor between this group and this group is x minus 1. So I have x minus 1 times x squared plus 2 equals 0. So when I set each of these factors to 0, I get x equals 1, and here I get x squared equals negative 2, and if I take the square root of both sides, I get plus or minus I times the square root of 2, which is not a real number, so it's just x equals 1. So this is my answer from step 1, x equals 1. Now when I move on to step 2, I'll be finding f prime of 1. So step 2, I find the first derivative of f of x, which is 3x squared minus 2x plus 2, and I'm finding f prime of 1 because that's the answer from step 1. I always find the first derivative of my answer from the previous step. So f prime of 1. And I place 1 in for all of the x's, and I get f prime of 1 is equal to 3 minus 2 plus 2 which is equal to 3. And when I get to step 3, I just take the reciprocal of step 2, so that the derivative of the inverse at the point a equals 4 is equal to 1/3.